This tutorial will illustrate how to set up a model for a response spectrum analysis in ETABS. However, before we do this, let's discuss what a response spectrum analysis is. Response spectrum analyses are typically used for performing seismic analysis. Response spectrum analysis calculates the maximum response values in each mode of the structure from a spectrum curve and then combines these responses using modal superposition. These input spectra might be for a smooth spectrum like codes used to describe a range of earthquakes, or spectra for a specific earthquake. Spectra curves classically plot period on the horizontal axis and acceleration on the vertical axis, and may consist of multiple curves for different levels of damping. A response spectrum analysis seeks to determine the likely maximum response of a structure when subjected to the pseudo-acceleration of a response spectrum curve. An easy way to idealize a response spectrum curve is as follows. A whole series of single degree of freedom oscillators at a given damping level are subjected to a time history analysis. The peak relative displacement values from each oscillator are determined and then converted into pseudo-spectral acceleration, PSA, by multiplying by the natural frequency squared. These points are then plotted on the ordinate against the period of the oscillator on the abscissa. Connecting these points leads to a response spectrum curve for a given damping. Our example here is for a single damping, let's say 5% of critical, but different curves could be generated for different levels of damping. This curve represents our seismic input. Response spectrum analysis is based on modal superposition. Modes of the structure are calculated, and then the corresponding pseudo-spectral acceleration for each mode is determined from the response spectrum curve that matches the damping of the mode. Converting the pseudo-spectral acceleration into displacement and then using the mode shape along with the modal participation factor, forces and stresses may also be determined for each mode. However, a building response is not made up of a single mode, but the response of many modes, so the response from the different modes must be combined. One way might be to simply absolute add all the responses together. This is not very realistic as it assumes all modes peak at the same time, same direction. A more common way is to combine the modes using some type of square root sum of the squares, a more statistical approach if you will. However, the squaring of terms means that the reported results will always be positive. So it is important to understand that these results can range to the negative values as well. In addition, there is no correspondence between two response quantities, like there would be in a time history analysis. With that bit of background, let's start our analysis. Our model will consist of a simple two-story, 1 bay by 1 bay concrete building. We start by determining what modes will be used. This is done using the define modal cases command. For our modal case, we can use either the classic eigenmodes, which are the free vibration modes, or the Ritz modes, which are load-dependent vectors. Ritz vectors are often a better choice when doing modal superposition, but for this example, we will stick with eigen. We will use the default mass source, which in this case is simply the mass of the structure, although other mass sources could be defined that might include things such as equipment mass. ETABS also allows for the stiffness used in the generation of the modes to be modified by P delta or a nonlinear analysis. In this model, we are going to use the stiffness as altered by P delta. And in this case, we'll use the p-delta determined from the non-iterative mass technique. We could also ask the program to determine static correction modes, which can be important when modeling supports that are very stiff. These are sometimes referred to as missing mass modes. However, we will skip this here. In the other parameters section, we can specify the maximum and minimum number of modes to be calculated. The response spectrum analysis will only use the modes that are actually found. Because our building is being modeled using rigid diaphragms, and we are not interested in vertical excitation, we will only have 3 mass degrees of freedom per floor, 2 translational and 1 rotational. Therefore, 6 modes should be adequate to capture the response that we are interested in, so the default of 12 should be fine. We could also adjust the range of the frequencies to be sought by using the shift and cutoff parameters. This could be useful if we want to force the program to search for building modes that are higher frequency, such as to match the input from a piece of vibrating
this
equipment.
Is the third and final part
However,
of this force
because
method
our
problem.
analysis is for seismic loads, the
the
lower frequency modes are important, and thus it is appropriate to use the defaults of 0.
But otherwise, we just spent
The
a very long
convergence
time
tolerance
doing force
determines
method.
how
Basically,
close
we started with this
successive
three-stack
eigenvalue
FE,
iterations
we
need
did
to be
superposition,
before the
then we did a
program
whole
can
bunch
move
of
on to the
non-area
next
method
mode.
stuff. All
For this case, the
carry
default
on,
is
took us a very long time
satisfactory.
to work through. Eventually, we found
Lastly,
some
we will
reactions, and
leave
then
the
we were
auto
left with,
frequency shifting option on. This
we
will often
finished
speed
off
up
with in
the
last videos. We
solution
had solved
and
all the
improve
reactions. We got
accuracy.
NA, AXAY, BY, and CY. Now the only thing we want to do now is
Next,
draw
we will
a shear
define
force
the
diagram
input
and
response
diagram
spectrum
of
to
this
be
problem.
used.
So if we draw a free body diagram of the very left-hand side, taking a virtual cut infinitesimally close to A, we know that we got
We
that
have
reaction
many,
here,
many to
AY
choose
pressing
from.
up, which is 19.6 kilonewtons. That means the internal shear right at that point has to be.
And in this case, we will use the ASCE 7-10 curve.
Right at that point has to be 19.
We will give the function the name ASCE
this matches our
RS.
positive sign convention, where for beams and bending we have the shears looking like that.
Note the function
and
damping
beams
ratio.
looking like
This
that. So we got
identifies
shear
the
pressing
damping
down on
used
the
to
right
generate
virtual
this
cut, so
curve.
we're starting at
If this
positive
value is
19.6
different than the
kilonewtons of
resulting
shear
damping used
in
for the
this
building,
region here.
this
So let's
curve
start
will be
here.
adjusted to match the
Maybe
damping
do a
level
straight line,
of
probably
the
a lot
structure.
nicer.
That
It's
is,
going to kick
if
us
the
out
defined curve we are
uninterrupted,
using
until
is
we
at
hit this point
5%,
load. So we're
as
starting
shown
at
here,
19.
but the modal
6
damping
kilonewtons.
we are using
And
for
then
our
once we hit
building
this
is
point load, this is going to
2%.
drop us down
The curve
50
will be scaled up
kilonewtons.
so that the
19.6
response will be
minus 50 is
greater
going to bring us down
with the
to
reduced damping
30.4.
of the
Let's
structure.
label this on.
For this response spectrum, the
30.4
parameters can be user-defined
All right, now this is going to go straight over
or determined
uninterrupted until
automatically
we,
by the
do
program
the
based on
reaction
either
dy,
latitude,
which is
longitude.
going to kick us up
or by
90.2
zip code.
kilonewtons. So
For this
maybe
example,
what
we
should do is
will
we'll label
use
this
user-specified
negative 30.4,
and
so
enter
negative
an S sub
30.4
S
plus
of 1.99
90.2 brings us up to 59.8.
and an S sub 1 of
So
0.65.
let's draw that on just like that. It's going to be somewhere
We
up
will
here.
adjust the site class to
And
C,
have
which is for
59.8
very
kilonewtons.
dense soil
And
and
the
soft
shear
rock.
drops linearly by 10 kilonewtons
Points for the
per meter
curve
over the
are
next
displayed
distance,
here.
The next span of 10 meters. So basically 59.8 minus 100 is going to
The
bring
period
us down
is shown
to
on the
negative
abscissa
40.2.
and acceleration in
Nice
G
and
units
linearly,
on the
to
ordinate.
negative 40.2, which is going to be somewhere like down there, and then we can
We
close
can move the
this
cursor
off
over
just
the
like that.
graph to
So
obtain
let's
the
label
coordinates
this
at
negative
any point.
40.2. And we're expecting that because the reaction here at CY is 40.2. And then we can kind of confirm that same thing if we just draw a little free body diagram, taking a virtual cut infinitesimally close but to the left of point C.
Next,
We
we
know that we
define a
have this
load case
reaction
to
here of
include the
40.2
response spectrum
kilonewtons going
analysis.
up, so that the shear here, the distributed load is going to be infinitesimally small if this distance x is infinitesimally small. So then all of the shear here right at the very end has to be
We will call the new
40.2
case
going down,
RS,
and that's opposite the positive sign convention.
and we'll select response
So that means it's a
spectrum
negative
as
shear
the type.
of a magnitude of 40.2 right at the end. So it looks like we've done that correctly. All right, so the next thing that we're
We
going
will
to need
apply
to
a
do is we need
response
to, we should have
spectrum
labeled on
as an acceleration in the U1
We've got
direction.
5 meters here for this distance. And then this
using
distance
the
here is not
previously
5 because
defined
this triangle is not symmetrical, but
ASCE
with similar
curve.
triangles we can
Next,
really
we will
easily
apply
find
a
that
scale
this
factor.
distance
This might be to
base of
convert
this
from
triangle
G
is
to
just
inch units, or to
5.98
apply
meters.
code factors such as
And then the
R
base of
over
this
I.
triangle is just going
We
to
are
be
also going to
4.2.
apply the same response spectrum
2
in the orthogonal U2
And then we want
direction.
to take the area of each of these. So
This
this
may
area is
seem
just going
somewhat
to be base
unusual,
times height.
but we will explain
so
our logic a
19.6
bit
times
later.
5 meters is going to be 98.
If we click the advanced
And this
checkbox,
area in here is just going to be 152. That's the
we
negative.
could adjust the
And the area
angle
of
at
this
which our
triangle, 1/2
functions
base
are
height
applied.
is just going to be 178.802. And then this area in here is going to be
The analysis will use modes defined by the modal case,
and this area
and we
in
have a
here
number
is
of
going to
ways
be
that we may
negative value.
combine the
It's going to
modes
be
for a
negative
given
80.
direction, including CQC,
0.802.
square root sum of the squares,
All right, these
absolute
units of
sum,
areas are all in
general
kilonewton
modal
meters.
combination,
So then when we come
and
down
others,
to the bending
but
moment
we
diagram,
will use the complete quadratic
we want to start
combination
off
here.
with the internal moment, but we already know what the internal moment is.
If we
going
wish
to be.
for the
So
amount
we come
of
back to
periodic
this
and
is the
rigid
free body
response to be
diagram of,
interpolated between F1
of
and
point A,
F2,
just
we
taking
can
vertical
check
cut
the
and
include
close
rigid
to the
response
right-hand side
checkbox.
of A. So if
In
we
order
also
for this
add on the
interpolation to
applied
occur,
moment, or basically
F2
the
must be
reaction
greater
moment,
than or equal to
it's acting on the
F1
beam in a
and
counterclockwise
non-zero.
sense, and
We
that
will not
was,
use this option here.
For some reason, I erased it
Since
here.
we are
It's
applying
44
excitation in
kilometers.
more than one direction in
from
a single
previous
load
videos.
case, we need to
So this was
specify how to
44
combine the directional responses
kilonewton meters.
using either
Now, if this distance in here,
SRSS,
again, if this
absolute,
is infinitesimally
or
small, then the force
CQ-C3,
couple, here,
we will
basically,
use
the moment
square root
it
sum of the
causes is
squares.
negligible.
Now we will
tends to
discuss
0,
why
so
we
that
use
means that we have
SRSS
internal
along
moment
with the same response
infinitesimally
spectrum
close
functions
to point
in
A,
both
of
directions.
44 kilonewton
Design
meters.
codes often require that
Going
members be
Counterclockwise, or
designed
going
for
clockwise on the
100%
right-hand side.
of the
And so when we
seismic
have it going
load
clockwise
in
on the
one
right-hand side,
direction
it's opposite the positive
and a
sign
lesser
convention.
amount,
So we're
say
starting
30
with
or
a value
40%,
of negative
in the
44
orthogonal
kilonewton
direction.
meters. So let's put it on about there.
However, to do this
Negative
effectively
44.
assumes that
Alright,
you
so
know
in
the
between this
critical
region,
direction
basically in
of
the
the
first
earthquake
5 meters,
motion,
we have this horizontal
well as
line
the
here,
principal
or constant
axes
shear,
of
so
the
it
building,
increases linearly
which
by
is
the
typically
magnitude
not
of
the
shear
case.
force diagram, and it's
In
increasing
theory,
because this is a
in order
positive
to
area.
capture
So
the
we have negative
maximum
44
response in a
plus
member,
98.
the
That's going to
orthogonal
bring us up to a
earthquake
value of
pairs
positive
should be
54,
rotated
which
through
should be
all
somewhere
possible
right
angles.
around there. So we have
A
positive
substantial
54
computational
kilonewton
effort.
meters. Now, as we traverse
However,
the next 5 meters, this
ETABS
is negative
offers
areas
a
we
better
then
way
subtract. It is
by using
constant
the
here, so
same
we have
function
linear
in
change
both
the bending moment
orthogonal
diagram. So
directions,
basically we have
and then using
54 minus
SRSS for the
152,
directional
and
combination.
that is going to bring
The
us
maximum
down to
may be captured
negative
using
98,
a
which
single
would be
analysis
somewhere,
run. And because this technique
there
is
or
coordinate system independent,
Alright, so we get
any
negative
orthogonal
98
orientation
kilometers
will
for
work.
the internal bending
A
moment
big
right at
time
B.
saver.
Now, in this next region, we have positive change because we have positive
For the
area,
damping, we
and,
have
but
a
because
number
this is
of
a linear
options,
section, we have
but we
actually
will use the
parabolic
default
curvature on
of
the bending moment
5%
diagram,
constant
and
damping.
and then we start getting negative change. Now, when we have negative 98 plus
Because our model utilizes rigid
178.802,
diaphragms,
that's going to
and
bring
most
us up
codes
to
require that
80.802.
accidental torsion be
And then the
applied
curvature
when
is the
using
same on
rigid
the way back down
diaphragms.
because it's the same slope.
We
of
will
this
apply
line, and
a diaphragm
80.802
eccentricity of
minus
5%
80.802
to both
brings us right
floors,
back down to 0, and
which
that
will
is exactly
apply
what
an
we were
additional
expecting,
moment about
basically
the
due to
center of
the
mass.
constraint, or not the constraint, like how the original problem was set up, which was right here, right? We would expect a 0 internal moment, basically, when we right at the roller reaction of a span like this. So there we go. We found the
Now we will
reactions,
switch
and then
off
we
the
just drew the shear
extrusions
force diagram
and get
bending
ready
moment
to
diagram
run the
of this
analysis.
original problem using the force method. Let's see if I can find where I had that. There we go. So we got the bending moment, or shear force diagram here. We got the bending moment diagram, and then we had all of the reactions.
We will run only the
Um,
modal
now,
and response
I think
spectrum
if you
cases.
have anything more than 1 degree indeterminate, the force method is a really slow and clumsy way to do it. You're better off using the slope deflection method or 3-moment equation. And I actually solved this exact same problem using those 2 different methods. And so I'll put
When
links
the
to those
analysis
also in
is
the
complete,
description.
the first
But
mode
make
is
sure you check those
displayed.
out as well, because I kind of think they're like a little bit better.
The second mode is another translational mode.
These, like, really long problems that are more than
The
1
third
degree
mode
indeterminate.
is rotational.
So, anyways, guys, if
The
you made
fourth
it through all 3 of these videos, then props to
and
you.
fifth
And I
are
really
both
hope this stuff helps,
translational.
because yeah,
And the
it's
sixth
definitely- it's
is
definitely
another
beats using
rotational
the force
mode.
method. So thanks for watching, guys.
Note that
and,
there are
good
no
luck
more
using
than
this
6
stuff.
modes, as we anticipated. 2 floors with 3 mass degrees of freedom. The response spectrum load case has the following deformed shape. It is a single response based on the superposition of the modes. We can show the base reactions by going to the Display Forces Supports command. We will select the two horizontal components. Note that the forces are symmetric. We can also view output in tabular form. Starting with joint displacements. Note that all values are positive. This is due to how modal results are combined. Returning to the tables, we will display diaphragm accelerations. Important for occupant and equipment studies. Returning to the tables once more, we will look at the participating mass ratios. Participating mass ratios denote how much mass we have utilized in our analysis. And the closer the summation is to 1, the better. Note that in our case, by the last mode, our participating ratios all do sum up to 1. This concludes this tutorial on creating a response spectrum analysis in ETABS.